So a very brief introduction to Professor Jeremy Melvin. Jeremy Melvin is an architectural historian, a curator, a writer, a journalist, and a regular consultant to the profession and broader audiences on the matters of architectural history, politics, and practice. He has held a number of key influential roles, including from 1996-1997, director of the Architecture Foundation, from 2000 to 2014, development of architecture program at the Royal Academy of Arts, and since 2007 to the present moment, he's a curator of the World Architecture Festival. There is a long list of amazing things that Professor Jeremy Melvin has been up to. So with it as a short introduction, it's a pleasure to have him here in this conference, presenting some closing remarks.
Thank you, Abel. Can you hear me?
Yes, yes, perfectly. And we can also see your...
You can see my screen?
Yes, yes, just perfect.
Abel gave a very flattering introduction. What he admitted was that I know next to nothing about digital computation. So why am I here? Well, digital computation, what little I know about it, I have to credit a brilliant maths teacher I had 40 years ago called Tristram Jones Parry. And he introduced me to the concept of dy by dx, in other words, differential and integral equations. And I think after some fierce but very effective teaching, I began to get some inkling of what it was about. And that has given me an underlying interest in the power of computation and its relationship to design, how they can come together. Because I think what TJP, as we all knew him, made us realize was that the same basic data can take you from a point to a line, to a volume, to a surface, to a volume. And therefore, you're already talking about some very basic design moves, even at the simple level of calculus that we are being taught as teenagers. So my interest then is not just in how design and computation come together, but I want to trace in a very sketchy way how they can relate, and especially how they might have potential for social benefit. And I've been taken by comments by Patrick Schumacher and his colleagues from Zaha Hadid's office about the social benefits that can come through digital design and computation. So I like to keep that in mind. But for me, this actually starts in the 17th century, in the scientific revolution, where there was a huge interest in trying to work out how theory and practice could come together. There had been some very serious theoretical advances in mathematics, obviously, from the 15th, 16th century, and there was an urgent need politically to think about how this new science, this new approach might solve some of the political problems that had come about across Europe, at least from the Reformation and the Counter-Reformation, the political upheavals that followed, and in the British Isles, the effects of the Civil War, which lasted from more or less 1640 to 1660, so again, the middle of the 17th century. And of course, that's more or less coincident with the 30 Years' War on the European continent, which devastated much of Northern Europe. So, but just to start, now this doesn't want to move on. Bear with me and I'll try and find out how to do this. Yes, there we are. It seems to me that the contemporary approach to digital computation and design starts with this building, obviously Sydney Opera House, designed in 1957 by Johan Utzon, finally completed in 1973 with Utzon in a rather ambiguous role. But the key players through this time were the engineers of Arup and Partners, particularly Arup himself, but working with Ronald Jenkins and Jack Zuntz, who were then very young engineers. And of course, when the architect designed it, when Utzon designed it, the famous sort of flowing image drawing, which was rejected in the first round by the jury, but revived from the waste paper basket, this is at least an anecdote, by a judge who came in late, Iro Sorinen from the United States. The architect had no idea how to build it. The engineers were then left with having to pick up the pieces. And that, I think, is a rather sad tale in the sense that it talks about two cultures. The culture of engineering, which is computational, and a culture of design, which is intuitive, free-flowing, imaginative. And it's been a rather unfortunate sort of barrier between the in the construction, I think, of buildings and the conception of architecture until relatively recently, but probably still existing in some areas now. But I want to start then, as I said, in the 17th century. This is, of course, René Descartes in a famous portrait by Franz Haus. Descartes lived for much of the entire first half of the 17th century. Born in France in 1597, died in Amsterdam. Died in Stockholm, having moved to Stockholm via Amsterdam in 1650. And of course, he's credited with some of the analytical geometry which leads into calculus, leads towards dy by dx. And I show here just a couple of diagrams on the right-hand side of the screen showing conic sections, how you can take the information derived from different geometric shapes and turn them into surface, into volume, and I think that's fundamental. Then this little image at the left, I couldn't resist putting it in. That's a picture of Tristram Jones Parry in front of a building at the school where he taught me, which was designed by the great British architect Lord Burlington, but after an original design by Christopher Wren, who was indeed educated at this school, along with Robert Hooke and John Locke, two other people who come up in the scientific revolution of the 17th century quite an important way. So, but of course, what Descartes was doing, Descartes and his contemporaries, was building on, as another of the contemporaries, Isaac Newton, said, building on the shoulders of giants. And here, of course, we're talking about the advances of the previous 150 years or so, notably Copernicus, who showed that the Earth revolves around the sun rather than what had been believed for millennia, that it was the other way around. In other words, the sun revolving around the Earth. On the top right, little image of a quadrant, which was the most significant navigational aid used by, or tool used by Christopher Columbus, who of course proved decisively that the Earth wasn't flat and you could sail beyond the horizon and not fall over the edge. And that was just at the end of the 15th century. So we're still talking about this sort of 100 to 150 year time frame before the 17th century and its scientific revolution really gets going. So the point about these two, Copernicus and Columbus, is that one, Copernicus, the great astronomer, mathematician, was theoretical. He was his work was largely theoretical, it's largely academic. And Columbus, who was above all practical, he may not have been a great mathematician, he may not even have been a great navigator, but he certainly showed how practically things could be changed. What they did was to overturn, as I said, the millennia-old beliefs in the flat Earth and the Earth being the centre of the universe. Now, one of the inheritors of this, not just Descartes, was this man, Francis Bacon, a very important, both a political figure, but also an intellectual figure in early 17th century England. Now, he came from a privileged background. His father was the second most important official under Queen Elizabeth I, and his uncle by marriage, in other words, the bloke who had married his mother's sister, was the most influential minister under Queen Elizabeth I, the great William Cecil, who becomes Lord Burleigh. So Bacon is born into a privileged establishment, but also a new establishment. He's not from an old aristocratic family, and although he's given a peerage, it dies with him because he had no children. But he was influential. So he was influential as a lawyer and a statesman. He was the Lord Chancellor for some years, but he was also a central figure in in establishing the groundwork for the scientific revolution in England. And because much of his scientific work is written in Latin, it was of course accessible across the whole of the Western world. Now, he is credited, I think, with the birth of the English tradition of empirical philosophy, and also with a very strong challenge to the predominant school of scientific thought, which despite Copernicus, despite Columbus, his practical discoveries, was still dominated by Aristotelianism. Now, it's important to note that that is a tradition in which Bacon, as a student at Cambridge, had been educated. He was very familiar with Aristotle, and in fact, one can think he takes the anti-Aristotle view further than he really did, because he was very respectful of Aristotle. What he didn't like was the way Aristotle's ideas had been completely unchallenged. He thought that you should always challenge orthodoxy. And as he says about Aristotle, this is a quote from The Advancement of Learning, "For as water will not ascend higher than the level of the first spring head from whence it descendeth, so knowledge derived from Aristotle and exempted from the liberty of examination will not rise again higher than the knowledge of Aristotle." In other words, if you want to go beyond Aristotle, you have to subject his ideas to examination, and very importantly, and this is one of the great innovations that Bacon makes, to experiment, to practical experiment. And although he died as a result of trying to make a practical experiment, he was fascinated by why meat didn't rot when it was frozen. And as an old man, he saw a chicken in a Christmas fair and there was snow on the ground, and he thought, well, I'll experiment with that. So the chicken had other ideas, and he had to chase it around Pond Square in Highgate, trying to catch it and decapitate it so it could be stuffed with snow. And as a result, he caught a chill and died from it. So, you know, he in a sense, although he wasn't known as an experimental scientist, he advocated it, and he really put his money where his mouth is, right to the end of his life. So the two things that apart from privileging experiment, that Bacon promotes is a knowledge of natural history, which basically he means what you can perceive yourself about the world around you, and the inductive method. So you take the information, the data, if you like, that you collect through your senses, and then use that and work backwards logically to understand the laws of nature. And that is a reverse of the scholastic approach derived from Aristotle that had been dominant for the previous few hundred years, if not 1,000 years, in European universities, which was that you assume that laws are there because they're set out by God and explained to some extent by Aristotle. We sort of gloss over the problem of Aristotle not being a Christian, but you work the other way around. And Bacon then suggests that the way to understand knowledge, the way you advance learning, to adapt the title of his book, is to work the other way around. Get the data first and then try to analyze it. And that is very much the founding ethos of the Royal Society, which started in 1662. That's some 35 years or so after Bacon's death, but he was still held up as a sort of great advocate of a particular way of learning, and his ideas had informed the people who went on to found the Royal Society. And from this, we don't just get the new science, as in physics, chemistry, and whatever, and mathematics, but we also, because of the collection of data and because of the need to make it useful, which is one of the key goals of the Royal Society, is to make this data and the way of analysing it useful, we also get the social sciences, as we shall see in a moment or two. Now, one of the people who built on Bacon was this man, John Wilkins. Now, John Wilkins was the warden of Wadham College in Oxford from 1648. He was a sort of loose supporter of Cromwell and the parliamentary side in the Civil War, but he was trusted by the Royalist party as well, many of whom sent their sons to Wadham because they thought they'd get a fair education there, which was quite difficult as a Royalist in other words. He also became Bishop of Chester. So he's not only someone who, perhaps it's fairer to say he's a promoter of scientists and scientific ideas rather than an actual originator of them, but he's also a clergyman. And this is quite an important combination. He is, after being warden of Wadham, he becomes master of Trinity College, Cambridge as well. So he has a pretty stellar career. He's also, and this is where his importance in science comes up, while at Wadham, he put together, or he encouraged to group around the college scientists who included Robert Boyle, Christopher Wren, Seth Ward, who was a mathematician and a bishop, Robert Hooke, and others. So he's he creates a nursery of the people who then go on to found the Royal Society, of which he is the first secretary. So his importance in this group is important. And he, in 1648, so the year he goes to Wadham, he published a book called Mathematical Magic. We can see the title page on the screen. And of course, magic with a K, an archaic form of spelling, but I quite like the coincidence it's a K, because if I remember my dy by dx, you always have to take the constant, which is represented algebraically as K. So here we have magic with a K, in other words, magic with a constant. Now this book, it deals with the mechanical powers, and in that Wilkins goes back to Archimedes, considered to be the greatest sort of mechanical engineer, for want of a better term, of the ancient world, and a real figure, he really lived, and automata. An obsession of the late 17th and 18th century, for which he credits Daedalus, who the great mythical craftsman, supposedly the creator of the labyrinth at the Temple of Knossos in Crete. Probably someone, or maybe a group of people who had some of the skills attributed to Daedalus did exist, but it's difficult to say really that that's the case. The book was very popular. It went through several editions in the second half of the 17th century, because I think it was quite accessible. And he talks about things like levers, pulleys, submarines and flying machines. And he records the story of an 11th century monk called Elmer of Malmesbury, an English monk, who reputedly created a flying machine which flew for 1 furlong, about 200 meters off the top of a church tower. And it took about, he was in flight probably for about 15 seconds. And in that, he was repeating the myth of Icarus, who we see on the bottom left here, the son of Daedalus, for whom he built a set of wings to escape from a prison. And of course, the legend is, and this is a cautionary tale about the benefits of science. The wings worked, he could fly, but they've worked so well that he wanted to try them out, and he flew too close to the sun, so being made of wax, they melted, and he fell into the Bosphorus and drowned. And of course, the other image here, which underpins his interest in flying machines, is one of Leonardo's sketches, Leonardo da Vinci's sketches for a flying machine. So Wilkins is in some ways in the mainstream of what the scientific interests were of his time and slightly before, but he does a lot to both popularize and advance this culture of experimentation and the use of instruments to do that experimentation, which is being developed not so much by him, but by the people under his aegis at Wadham: Boyle, Hooke, the great instrument maker, Wren, and others. Now, but this has, I think, shows, sorry, I want to move on to the next image. Sorry, this is the flying machine, the human-powered flying machine eventually realized, the Gossamer Albatross, very lightweight aircraft, which did finally fly across the English Channel, a distance of 21 miles or whatever that is in kilometers, 35 kilometers or so, in 1979. In other words, it took 1,000 years or so, 900 years after Elmer of Malmesbury, and several hundred years after Leonardo da Vinci and John Wilkes to achieve something that really became a practical flying machine. But is it as practical as a Boeing 747 in its social utility? Almost certainly not. Now, one of the people who was based at Wadham in the 1650s, he'd been a student and then became a junior sort of lecturer, a fellow of the college, is the man on the bottom left, Christopher Wren, best known as a great architect, the architect of St. Paul's Cathedral and the great city churches around it. And that's in a famous portrait. Towards the end of his life, you can see his hand is covering the plan of St. Paul's by Godfrey Kneller, the late 17th century portraitist, leading portraitist in England at the time. But one of his earliest excursions into architecture was this building that we see in the images on the left, the Sheldonian Theatre in Oxford. Now, the Sheldonian Theatre was conceived in the 1650s, and this is while the Civil War has calmed down and England is ruled by Cromwell, the leader of the Parliament, the victorious parliamentary forces. But his regime is creaking around the edges, and in fact he dies in the year that this building starts, in 1658. And the building itself, which was named for the University Vice-Chancellor, who was a royalist called Gilbert Sheldon, hence Sheldonian, he revived an idea by an earlier Vice-Chancellor, the Archbishop William Laud, who was a very, very strong supporter of royalism and was executed by Parliament because of that, which was that the university should have a building dedicated to graduation ceremonies. What happened at Oxford before this was built, I don't really know. Obviously, people did graduate, but here there was to be something that would be a celebration of the event of graduation. And it was to be a temple, a theatre, and the theatre building type, notwithstanding the Globe and other commercial theatres which had been around for between 50 and 100 years by this time, was the great classical amphitheatres, all of which were open air. So in the climate of England, even Oxford has a relatively clement English climate, you need a roof. And if you want to do a building that sort of recalls a classical theatre, you have to have a roof that isn't a really steeply pitched roof. And the building, for functional reasons, had to have a clear internal space, no columns, in other words. So Wren, who was already making a reputation as a mathematician, was asked if he could come up with a way of solving this. And Wren draws on the work of someone called Thomas Willis, a mathematician, who maybe 20 or 30 years earlier had proposed a geometrical flat floor grid, which we see, I don't know if you can see my cursor here. And that means that you can span a greater distance without having to have a really high truss. This is what Wren put into operation. It worked. In fact, it was so strong that the Oxford University Press stored, or was it the Bodleian Library, stored books on top of the truss below the roof line. And 100 years or so afterwards, there was concern that this weight would be damaging to the building. But indeed, it was found to have shown remarkably little structural movement, although the books were moved. But it was, so it's, in a sense, a triumph of innovation through what then was the most advanced digital computation. And Wren, of course, is a key figure in architecture, also a key figure in the history of science. He wrote much of he was a founder member of the Royal Society, wrote much of its charter. And, he was a serious mathematician and also an experimenter. And this combination of science and experiment is, I think, a really important thing among this group of people at the time in the 17th century. But just as a little excursion into more architecture, of course, this scientific line of thought had a big influence, and it influenced the great rationalists of 18th century France. And here we see one of the most notable celebrations of that, the famous cenotaph for Newton, designed by the French architect and architectural sort of thinker, Etienne Louis Boullé, and it dates from 1784. And here you can see the scale of it, because this is a human being. And this is obviously the celebration of Wren, not of Wren, of Newton, who, there's a famous rhyme, which is all was darkness until God said, let Newton be, and all was light. And this is always trying to demonstrate that it is not quite clear what the light source is, other than that of Newton's thought. It's clearly nighttime outside because you can see the stars. There's a little bit of smoke in here, so we can imagine Freemasons being involved, rituals. But anyway, that is one end in architectural terms of the scientific revolution. Now, to build that, of course, you would need to have digital computation, which wasn't possible at the level of power needed in 1784. It wasn't a practical building project. But also coming from this sort of process of rational thought is a building that, or a series of buildings that were built, or at least partly built, designed by Boulé's contemporary, Claude Nicolas Ledoux, for the salt works, the royal monopoly on salt, Arc-et-Senans, in eastern France. And of course, it was built originally as a buildings as direct to the saltworks house. These are various ancillary buildings, a very massive and grand entrance, reminiscent of the barrière that Ledoux designed around Paris as points to extract tariffs on goods going in and out of the city, all of which contributed to the royal coffers and were resented by the revolutionaries as such. But what Ledoux is doing here, again, is building on the rational thought that derives to a great extent from Bacon and Bacon's followers in 17th century England, and then is developed by the great philosophe of 18th century France, Voltaire, Rousseau. And this is obviously a series of buildings which are known for being expressive. But they're expressive of what? Of royal power, because that's what they were there to serve, to reinforce the royal monopoly on salt, which was an essential commodity at the time. Or is it expressive of Rousseau and nature, Rousseau's ideas about nature? So what we have here, I would say, is a combination of analogy, of language, and of synecdoche, a figure of speech, rather than a embodiment of a digital computational principles in architecture. So a little excursion there. Now we're back to digital computation, and another contemporary of Wren and Wilkes and Newton and Hooke and Locke, this man William Petty. Now, William Petty was again on the fringes of the group at Wadham around Wilkes. He had a very strange background. He came from a family of clothiers, of cloth merchants in southern England. He went to sea at the age of 14, broke his leg, so the captain of the ship put him ashore in northern France, where he thought, well, if I can't be a sailor, I might as well try to be a bit of an intellectual, and I need an education for that. So he wrote to the local Jesuit college begging to be admitted. The fact that he wrote it in Latin, wrote his application in Latin, probably had something to do with him being accepted. And that started him on an intellectual journey, which was very varied, but very interesting. Because although he was educated by the Jesuits, he never became a Roman Catholic. When he left Jesuit college, he went to Amsterdam, where he got to know Descartes. So this is sort of in the 1640s. He obtained an invitation to Thomas Hobbes, the great English political philosopher, who was then in Paris. And he seems to have been Hobbes's secretary for a period. And then he went to Oxford, where he worked with Boyle, Robert Boyle, the scientist, as basically as a sort of paid assistant. And he qualified in medicine at the time. Now, the interesting thing about Petty is that he was trying to understand the interrelationship between politics and economics. And this is very much the project that Hobbes had been engaged with. And I think one can detect a lot of influence of Hobbes in this. He wanted to use mathematical thought to inform how political decisions can be made. He wrote this book here, Political Arithmetic. Sounds a bit like mathematical magic, but I can tell you it's not magic, which was about how do you collect data about what we would now think of as economic data, and how do you analyze it, and how can you use that to inform decisions to bring about, this is a quote from Hobbes, civil peace and material plenty. In other words, this is the fundamental project of politics and economics, more or less since that time. Now, political arithmetic sets out a way to try and do that, to make sense of data and the challenges which lie in data, but aided by mathematics. Now, unfortunately, it's not quite as good as it sounds. His only real mathematical operation is to find the mean of any set of data, which I don't think is necessarily the most useful thing to have. Now, he was influential. He was also a member of the Royal Society. He gathered together a huge fortune because he managed to work out a cheaper way of surveying Ireland after Cromwell's invasion of Ireland in the 1650s. And he, for some reason, don't quite know how this happened, quite a lot of Irish land ended up in his hands. And it is the basis of the family. He founded his descendants and Marquesses of Lansdowne, who are still big landowners in Ireland, and have supplied several statesmen and at least one prime minister. But what does Petty contribute to architectural design? Well, actually, I have to confess, very little. Apart from his theories of urban growth. He's interested in how and why cities might grow. And in that, he influences another early economist and but a practical property developer as well, called Nicholas Barbon, who was born in around 1640 and dies in about 1698. Don't think dates are precisely known. But of course, it then that line of thinking about understanding how my cities grow and how we can use data to understand that and manipulate it. I mean, Barbon is very interested in how the city can become the economic engine, and the economic engine can then become the source of power for the state. That line of thinking leads into people like Thomas Malthus 100 years later. So this is why this line of inquiry started, which seems to start, I think one has to be a little bit careful about saying there was some way to magic wand to start it, but seems to start with Francis Bacon, then leads not just into the hard scientists, but also into the social scientists, because it's based on the collection of data. And Petty is a central figure in that. Now, unfortunately, we're jumping forward several hundred years here, because of course that is one of the conceits of modernist architecture, is that you can design for social purpose because you can collect and you can understand data. You get it in early modernism in the 1920s and 30s, but perhaps it was reached its peak in the sort of work that was being done around the formation of the welfare state in the United Kingdom in the after the Second World War in 1945 through to the 1970s. And a key moment in that is a publication of this pamphlet by the Fabian Society, which then was what passed for the intellectual end of the Labour Party, called Architecture, Art or Social Service. Now, you may already have guessed that the question mark is redundant. It was very clear to the author, Paul Thompson, who was at that stage based in Oxford, but became Professor of Sociology at the New University of Essex. And this is 63, this is published 1963. That architecture should be a social service, as we get from these little quotes. He's very enthused by the school building program in Hertfordshire, which then extends to other counties, but Hertfordshire was the pioneer of this in the late 1940s, which were, quote, based on a knowledge of educational method and theory and the needs of teachers and children. And he goes on to say, left to themselves, architects will ignore the revolutionary concept of architecture in the Hertfordshire schools, because the instinct of nearly every architect is to sacrifice convenience for superficial beauty. Well, those architects among the audience may find that rather an insulting phrase, but I think the point about it is that it betrays a way in which architecture was seen, not necessarily practiced, but was seen, that architecture is about building monuments, not about building things that are practically useful. So in that sense, denied this founding ethos of the scientific revolution and the Royal Society. Now we can see something similar, but perhaps slightly more sophisticated in the work of this man, Richard Llewellyn Davis, Professor of Architecture at the Bartlett from, I think it was 1960, he was appointed until 1975. A very, very influential figure. His cousin was the model for Peter Pan in the play. He himself was educated at Eton and at Cambridge, where he knew and may indeed have sympathized with the people who became the spies, Burgess, Philby and Maclean. He was friendly with a group of old Etonians who included Victor Rothschild, father of Jacob, the present Lord Rothschild, and also a man, sugar baron, called Jock Campbell, who became the chairman of the first chairman of the Milton Keynes Development Corporation, which in effect created Milton Keynes. And guess who was the master planner? Well, it's about as mysterious as how William Petty managed to end up owning quite a lot of land in Ireland. But Llewellyn Davis was perhaps more interesting than that suggests, which is that he did bring a formidable intellect to bear on some of the practical problems faced by architects on a much bigger scale than just schools. And we see here, and I apologize for being quite small, this is a diagram of Northwick Park Hospital, one of the major hospitals of a significant number, which he and his firm, which eventually became Llewellyn Davis, Weeks, Forrester Walker and Bohr, designed. They were known both as master planners, Milton Keynes and others. They did a lot of work in Iran, for example, much of which was overseen by Walter Bohr, who was a Czech-born planner, and the other area which John Weeks seems to have been one of the sort of guiding force was in hospital design. And this is hospital design at a point where medical science is advancing enormously, and medical provision through the National Health Service, created in 1948, is also advancing. So this generates a need for new and different hospitals which can deliver the benefits of that, both the funding and the scientific advances in healthcare to the population. Now, they had two basic ideas, Llewellyn Davis, Weeks, Forrester Walker and Bohr. The first was put into action at Northwick Park, which was the principle of indeterminacy. Now, that in effect was, well, we might be able to understand if we work very hard on what medical care is now. What we don't know is what it will be in 5, 10, 20 years' time, in other words, within the lifetime of this building. And therefore, the building has to be infinitely extendable, less adaptable, more extendable. So it was based on a standard cross-section, which could then be extrapolated over any, theoretically at least, over any distance. Now, I've only been to Northwick Park once to see a friend who was there, and I have to say it was a pretty dispiriting experience. So there wasn't a great deal of thought about really the patient, but certainly not about the visitor environment. Now, the second idea that Llewellyn Davis, Weeks, Forrester Walker and Bohr had about hospitals was to minimize the distance between the ward and the operating theatre, because studies had shown, and Llewellyn Davis was a great fan of social studies. In fact, he brought social science into the Bartlett, and as some Bartlett graduates may know, and some of the older ones may even remember, these studies had shown that a great drain on resources was the moving of patients between the ward and the operating theatre. Minimize that, and the theatre can function better, the patient can recover more quickly, and all sorts of other benefits would flow from it. So that's a science-based sort of innovation in hospital design. Now, Llewellyn Davis's partner, Gwent Forrester Walker, wrote, sort of thinking about hospital design, the architect for a hospital has to design a building to house quite an exceptional number of interrelated but different functions, many of great complexity. His building has to take care of the processes which rage over the medical, the domestic, the commercial, the social, the industrial, and the scientific. All these he has to include, sorry, it is he, because at the time it almost always was he, to include in a building which must be of visual quality and which can take its place as something civilized in the surroundings and life of the community. Forrester Walker there is recognizing that design, or the visual characteristics of design, are important as well as the functional ones, something which I think few would think their work really achieved, although the sentiment is clearly there. But I think the point I want to make about this is the plethora of information from all sorts of different angles, you know, as he says, the medical, the domestic, the commercial, the social, the industrial, and the scientific, not necessarily compatible. And somehow the architect has to compute that into a workable design. Now, you could say, well, that's just what architecture is. And someone who did is the man sitting down in the center of this image, the great American postmodernist Charles Moore, born in 1925, died in 1993, in front of one of his most famous buildings, Sea Ranch condominium on the California coast, built in 1965. Now, we don't normally think of Charles Moore as one of the pioneers of digital computational design, and he wasn't, because what motivated Moore was a great intuitive sense and an ability to understand not just sensory perception, but by how other people might understand it. And I think he did that by and large intuitively. I didn't know him and I haven't seen many of his buildings, but he wrote a very interesting essay in the 70s, called 11 Agonies and 1 Euphoria. And in it, he says, quote, that design is that combination of research and understanding and intuition and improvisation which tries out solutions in too many unknowns to be susceptible of solutions by the disciplines based on logical words. Clearly he has left out punctuation there deliberately, which makes it quite difficult to read. And he goes on, if we can lose the agonies attending our professional hang-ups about revolution, relevance, ineffectiveness, hierarchy, advocacy or arrogance, divine right, racism, inefficiency, failure to reproduce, isolation and certification, which sort of sums up many of the hang-ups about architecture, I think, we will have left in our province one of the key tools to the solution of the world, design. And so design is therefore the euphoria among the 11 agonies, of which he alludes to earlier in the quote. Now, clearly Moore is not synthesizing all those problems, all those agonies, as he terms them, in a computational way. He is chasing perhaps a goal that also eluded William Petty and Llewellyn Davis and the Fabians and almost everyone else up to that time. What he achieves in terms of magic in design, and I think he does achieve magic. I mean, this is an interior Sea Ranch on the left, then there's the faculty club and the University of California at Santa Barbara, where he designed much of the campus, was about permeating experience of the user. Very human-centered. He was, I think, it's fair to say, not a term I feel particularly comfortable using, a great humanist. But he wasn't a great mathematician. What he did was to privilege experience. And where I think Llewellyn Davis and his colleagues were about trying to understand rational and abstractly conceived processes, more foregrounds of human experience. And to me, that suggests he is at the door of what people like Schumacher and his colleagues are arguing is where computational design can now take you, and beyond what the computational design in the hands of engineers delivered at Sydney Opera House. So I just want to end with this image, I'm sorry, nicked from the website of the Shirbank Technology Center in Moscow, which Patrick describes, and he uses these words, quote, we see users as sentient, socialized actors who use a built environment as an orientating matrix where myriads of social protocols are inscribed. So there, Schumacher is trying to suggest that the building form is not just an analogy, it actually is integrated. The experience is integrated into the form. But I think that is not a million miles from the intuitive designs achieved by people like Charles Moore. And I don't think I don't want to leave out others. I just think Moore articulated it so beautifully. And I would say watch this space, i.e. people like Zaha Hadid architects, for more mathematical magic, but perhaps this time without the K. Thank you.
Thank you very much, Professor Melvin. That was a wonderful, wonderful presentation. And it's with a lot of gratitude that I thank you, all the authors and all the presenters yesterday and today, and all the advisory panel in this conference.